So that should let me flip through the slides. Or anyway. Sorry, good to go? Oh, okay. All right. Good morning, everyone. I would like to welcome you on behalf of the Electrochemical Society Student Chapter of Purdue to today's symposium, MoChA, Modeling, Characterization, and Analytics in Energy Storage and Conversion. Let me start off with a quick look at the energy flow diagram. This is my favorite one. In today's context, at least, let me make a few comments. Electricity is the most useful form of energy. Second, in order to have widespread electrification in the transportation sector and also renewable energy integration into the grid, we definitely need energy storage. More so, toward achieving the goal of decarbonization, electrochemical conversion pathways or systems could play a big role in the sectors which are hard to decarbonize, such as steel making or cement. Also, building energy. And please note that electrochemical systems and pathways do offer overall improvement in energy efficiency. With that, we are in the era of electrification of things, EOT. One thing is clear, and it's undeniable, that electrochemical energy systems, conversion and storage, electrochemical pathways, electrochemical mechanisms and processes are going to play a major role in electrification of things, whether it's the ground transportation or aviation or renewable energy integration into the grid or decarbonization of hard to decarbonize in sectors such as manufacturing of steel and cement. I do not know what could be a clear winner, but there are a mix of electrochemical technologies are going to play a major role, as you could see here. What we need, certainly, to understand fundamentally what's happening in these systems. They are diverse systems, but also they have certain commonalities. We want to understand things at the materials level, architectural level, and we integrate what's happening at those fundamental processes and mechanisms and scales to the system metrics: performance, life, and safety. For that, we need MoChA, physics-based modeling, multimodal characterization, and high-resolution experimental analytics. With that, let me welcome you again to today's event. Let's enjoy some MoChA. Thank you.
So we have a short video message from Dr. Judy Jeevarajan, Distinguished Industry Advisor to our chapter.
Good morning. I'm Judy Jeevarajan from UL Research Institutes. I lead the Electrochemical Safety Research Institute there. And I would like to welcome all the students and participants to the symposium, POSIS Symposium, hosted by the Modeling, Characterization, and Analytics in Energy Storage and Conversion student chapter at Purdue University. The student chapter has done a lot of very good programs in events in the last couple of years. They hosted a program with women in electrochemical science and engineering and had many leading women scientists and electrochemists speak in this webinar series. They also held a webinar series on solid-state batteries, which was very well attended and was very informative. So I would like to thank the student team for putting this poster symposium together. And it's an in-person event that is happening after a couple of years of having virtual events. So I would like to congratulate them and also wish them luck. I hope you all enjoy this symposium, poster symposium, and learn a lot from it. Thank you.
Good morning, everyone. Thank you, Professor Mukherjee, and thank you, Dr. Jivarajan, for this wonderful introduction. So I'm Debanjali Chatterjee, PhD student in Purdue Mechanical Engineering and president of the Purdue Student Chapter of the Electrochemical Society. I would like to begin by giving a brief overview of our student chapter, our student executive board and advisory committee, and our past activities and achievements. The ECS Purdue Student Chapter was founded in May 2019 with the aim of promoting discussion and collaboration between electrochemistry and solid-state science students at Purdue University and the Greater Midwest region. Professor Partha Mukherjee from Purdue Mechanical Engineering is our founding and lead faculty advisor. Other members in the advisory committee include our distinguished industry advisor, Dr. Judy Jivarajan, Vice President and Executive Director, Electrochemical Safety Research Institute, UL Research Institutes, Professor Rebecca Chase from Purdue Mechanical Engineering, and Professor Julia Laskin from Purdue Chemistry. The chapter is led by me, along with Vice President Aditya Singla, Secretary Shorim Banerjee, and Communications Director Anu Alujage. Over the past 2 years, the ECS Purdue Student Chapter has established itself as one of the leading student organizations for scientific outreach in the field of electrochemical energy storage and conversion. In 2021, with the COVID-19 pandemic threatening to disrupt all scientific collaboration and communication, we used the power of virtual communication platforms and social media to launch our signature webinar series, Women in Electrochemical Sciences and Engineering, or WISE. Comprising talks by 14 prominent women electrochemists from academia, national labs, and industry, this series was dedicated towards highlighting the hugely impactful research and academic journey of women scientists in the field of electrochemical energy storage and conversion. In addition, it was an important step towards addressing several deep-rooted issues in our society with regards to diversity and representation in the energy resources space. WISE received a phenomenal response from the scientific community, culminating in an invited energy-focused article in ACS Energy Letters, celebrating women in electrochemical sciences and engineering. Our next theme was on one of the most promising candidates for next-generation energy storage, solid-state batteries and electrochemistry. With webinars by leading experts in this field, this series received critical acclaim and saw record webinar attendance, not only from the US and Europe, but also from India, Australia, and the African continent. Our ongoing theme is MoChA, Modeling, Characterization, and Analytics in Electrochemical Energy Systems. Started in 2022, we had webinars on a plethora of topics, ranging from modeling and computational design of batteries and characterization techniques for interfaces to fuel cells and the hydrogen economy. As the COVID-19 restrictions were lifted, we brought back in-person seminars after a 2-year hiatus. For our efforts towards advancing scientific collaboration, education, and exchange of ideas, and promoting scientific outreach on a global scale, we received the ECS Chapter of Excellence Award in 2021, followed by the highest distinction, the Outstanding Student Chapter Award in 2022. Our initiatives and achievements were featured in the ECS magazine Interface and recognized by the Purdue research community through a feature article in Purdue Mechanical Engineering. I would like to thank Dr. Judy Jivarajan, Vice President and Executive Director, Electrochemical Safety Research Institute, UL Research Institutes, for supporting and sponsoring today's event. We also thank Professor Partha Mukherjee, Director of the Energy and Transport Sciences Lab, ETSL, the School of Mechanical Engineering, Purdue University, and the Electrochemical Society, ECS, for their support, guidance, and sponsorship. With that, I welcome you all to the MoChA Poster Symposium on Modeling, Characterization, and Analytics in Electrochemical Sciences and Engineering. I would first like to invite Professor Rebecca Chase to officially begin this event with her plenary talk. So before we begin, I would like to give a brief introduction to Professor Rebecca Chase. Dr. Chase is an assistant professor in mechanical engineering and Environmental and Ecological Engineering at Purdue University. Her research focuses on how energy systems, including transportation, electricity, and industrial systems, can work together to transition to a decarbonized future. Using systems analysis approaches, her work draws upon methods from engineering, policy analysis, and economics. She holds a bachelor's degree in mechanical engineering from Columbia University and a PhD in engineering and public policy from Carnegie Mellon University. Professor Chase, we look forward to your talk.
All right, well, thank you all for being here and for the kind invitation to speak. I'm glad to be back in person and to meet so many of you today throughout the course of the event to go over and learn more about all of your research. And so today I want to talk about, and maybe my pitch to you as students, how electrochemistry broadly can contribute to this decarbonized future that we want. And so, again, sort of touching on some of the themes that Partha mentioned earlier today, today's energy system as it stands is still largely dependent on fossil fuels. And so this is US primary energy consumption in 2021. And so as you can see, petroleum is still the largest single source of energy. So we've got petroleum, natural gas are both fossil resources, but we've made some progress. So renewables now account for about 12% of our energy production, and so they've overtaken coal. So we've beaten one of the fossil fuels, but there's still obviously a long way to go to growing this to have more decarbonized resources. And so I also love a good Sankey diagram. So when you look at where that energy is going, we are putting a lot of those resources into producing electricity. So there's a lot of natural gas, especially that's going to electricity production, residential and commercial, so heating homes and buildings, and then industrial use as well, with petroleum contributing for transportation mostly. And again, to highlight that there is so much of this energy is currently being rejected. So we're only delivering a relatively small portion of energy services from all of this input primary energy that we're consuming. And so if we want to beat that, we're going to have to change the way that we operate this system. And so that change is happening. And so if you look at what's planned for this year, and what kind of power plants we're expecting to install, the vast majority of those plants are supposed to be solar, right? So over half is supposed to be solar power. There's substantial contributions from wind. There's a little bit of nuclear that's expected to come online. And then significantly battery energy storage is expected to be about 17% of what's installed in a power capacity, which does exceed the expected construction of natural gas. And so we're on this trajectory where we're going to have these more renewable resources, and there's obviously a role for battery storage, but what other sort of resources can we use in electrochemical resources can we contribute, considering the climate needs that we're facing? So as you can see here on the left, these are just atmospheric concentrations of CO2. And so that's the blue line, and you can see it's been increasing pretty steadily and rapidly in the recent decades. And that's because we've been emitting more CO2 on an annual basis. And so that's the darker gray line. If you do on a cumulative basis, most of the CO2 has been emitted, about half of it has been emitted since 1990. And so that's not that long ago to have done a lot of this have a lot of these emissions. And so CO2 persists in the atmosphere. So it doesn't degrade for hundreds of years. And so the stuff that we've emitted is the stuff we're still stuck with. And so we've done a lot of damage in a relatively short amount of time. And if we want to undo that and not avoid the most damaging and high temperatures of climate change, which are these sort of red and yellow scenarios here on the right, we have to have a rapid decrease and then to zero and then net negative CO2 emissions by about mid-century, right? So if you think about 30 years ago when it was 1990 and about 30 years from today when it's 2050, we're going to have to make these rapid changes if we want to avoid the worst effects of climate change. And so how do you get to net negative from this scenario? And so a lot of that will be to stop digging the hole any bigger. And so we talked about transportation and battery energy storage can play a significant role. So looking at just most recent sort of sales data from the United States, From all of the vehicles sold, like passenger vehicles sold, about 7% of them were electric vehicles last year. So that's a pretty high percentage. We've made a lot of progress. But we still need to continue to improve the energy and power density of these battery materials, not necessarily because we can't build a passenger vehicle today that does all these things we want it to do, but we need to expand the types of vehicles that we can use these batteries for. We need to be able to use energy storage in other vehicles besides passenger cars. We also want to use materials more efficiently, right? So these are a lot of cars that we need to put on the road. And so if we can use the materials and store more energy in those materials, it'll be less expensive. And then it's not so much that you can't drive a car fast enough with today's power density, but really we want to solve the challenge of charging, right? So if you can have a vehicle that charges much faster, you can have a smaller battery than you would otherwise because people aren't as worried about being stuck on the side of the highway because they ran out of juice on their road trip. And so as we start to think about expanding these processes and these transportation resources, we also need to, in parallel, develop recycling methods and recycling pathways that can efficiently recover those materials, right? You spend all of your time researching better battery materials, and you put a lot of effort to make them as advanced as possible. And then today's recycling processes are basically, you combust it and you melt it down and you start over. And so you lose and you actually create a lot of emissions through those processes. And so we need to develop better circular economy metrics that can recover those materials more efficiently. And so it's not just transportation. Electrochemical storage obviously can play a role in longer duration grid storage. So we're installing batteries today. And so the batteries that we might want for longer duration storage will probably be different than the batteries that you would want for a car, right? So we have these daily and seasonal cycles of how we orbit the sun. And so we should be designing batteries that are most appropriate for those kinds of applications. And so things like chemistry and form factor can be make these types of batteries more competitive with their fossil fuel counterparts. And then, as Partha also mentioned, what do we do about all of this other stuff, right? So we've taken care of electricity and transportation, but there's so much other energy that we consume for different resources. And so hydrogen electrolysis can help in a lot of scenarios to replace fossil fuels in many industrial processes. Things like electrocatalysis could also help produce synfuels, right? So putting a battery in an airplane, maybe not the most feasible solution, but potentially you could produce synfuels that you capture carbon and use that as your carbon source and use electrocatalysis to help with those processes. And then there's other goods like plastics and fertilizers that we manufacture in really large quantities that become big sources of overall emissions and could also be a potential pathway for electrochemistry. And so then my final sort of pitch is that the plot I showed you showed negative emissions. So it's not enough to just stop digging the hole. You have to actually go and remove the previously emitted gases. And so there are roles for electrochemistry in this space as well, right? So you do these reactions to capture that CO2 from whether it's a process that's emitting CO2 or just ambient air, direct air capture. And so once you've captured it, you have to regenerate that material so you can reuse it over and over again if you want to reach the CO2 capture requirements to reach those net negative targets. And so there's a lot of need to rapidly assess, test, and rethink sort of system designs that are most appropriate for these decarbonization and direct reduction methods. And so with that, I'll just say thank you and open up for questions if there's a little bit of time.
We can have a quick couple of questions.
Thank you. So my question is, since in the next 20, 30, 40 years, a lot of the carbonization is going to be coming from developing countries that are trying to modernize, industrialize. And it's a lot cheaper for them to use fossil fuels. So even though we fix our own problems in the US, Europe, other first world countries, how can they do it efficiently too?
Yeah, and so I think the question about whether it's cheaper and it will be cheaper for forever to build new carbon-emitting sort of energy infrastructure. That picture is changing, and it changes more and more as these kinds of technologies become less and less expensive, right? So as solar and storage potentially could become less expensive and be more widely adopted, or at least competitive with other fossil resources, it is a challenge, but I think realistically there are a lot of other considerations that perhaps, like you do, allow people in countries that have contributed more to sort of the carbon balance that as it exists today may have different responsibilities than developing countries that are still building out energy infrastructure.
Hi, good morning.
Yep.
So I think I have two questions. So the first one would be regarding the hydrogen economy, like which application do you think that are more suitable to use hydrogen instead of just electrifying the system? And then on the other hand, I would like to know, in your opinion, how can we deal with the challenges of actually building a hydrogen infrastructure in different
Yeah,
countries?
so hydrogen is challenging because it is so tiny, right? And so we have a lot of challenges building like methane infrastructure. Natural gas infrastructure has a bunch of challenges. It's very leaky to people's homes. I think that would probably be a challenge.
So that's all the time we have for the questions. So thank you, Professor Chen, for giving us a wonderful, So thank you, Professor Ches, for giving us a wonderful perspective on decarbonization and the role of electrochemical energy storage in solving this problem. So hello all, I am Aditya Singla, the Vice President of the ECS Purdue Student Chapter and a PhD student in the Department of Mechanical Engineering here at Purdue. So now we would be moving into more technical presentations with three student keynote presentations. And the first student speaker that we have today is Susmita Sarkar. So Susmita is a PhD candidate in the School of Mechanical Engineering here at Purdue University. Her research focuses on exploring science, chemistry, and mechanics to design and manufacture next-generation energy storage devices and improving the performance, reliability, and yield of the existing battery chemistries. She has received numerous awards and fellowships, and I won't be able to list them all here, but let me try to list a few of them. She received the Bilsland Dissertation Fellowship and Ben M. Helbury Graduate Scholarship from Purdue University, Best Presentation Award in Student Battery Slam in the Electrochemical Society ECS meeting, Outstanding Graduate Student Member IEEE, and was also selected as a Rising Star in Mechanical Engineering organized by MIT. She is also the founding president of the ECS Student Chapter at Purdue University, and under her leadership, the chapter received the Chapter of Excellence Award by ECS. She was awarded the Homer Engineering Excellence Fellowship and Outstanding Service Award from Purdue College of Engineering for her community engagements and contribution to diversity. With this, I present to you our first student speaker, Susmita Sarkar.
Good. Okay. Good morning, everyone, and welcome to the symposium organized by the ECS team at Purdue. And first of all, I would like to congratulate the entire ECS team for putting up such an excellent event. And it's my absolute honor to give a talk in this chapter. And my name is Sushmita. I'm a PhD candidate in the School of Mechanical Engineering, working under the supervision of Professor Mukherjee. And what I hope to talk today about mechanistic complexation in sodium-ion battery electrodes and how I alleviate those. Now, a grand challenge for the 21st century is increasing energy consumptions worldwide. This could be due to the increasing urbanization, rapid growth in the burgeoning economies around the world. Now, our challenge is to improve the quality of life without linking it to the carbon emissions, because that could potentially lead to the global climate change. We have been making progress, though, for the last 10 years or so. We have been relying a lot on the renewable energy storage. Solar, wind has seen a lot of dramatic reduction in the cost. Now, as we are going to be relying on these kind of intermittent sources, we are going to be challenged by when the electricity is available, since we won't have the sun or wind available whenever we need them. So what are the solutions? Now, we need some sort of cost-effective energy storage. Now, there exists a lot of different kind of energy storage, but today for my talk, I'll be mostly focusing on the electrochemical energy storage. So we all know that the energy storage is not only, we are all familiar with the lithium-ion battery that is in the portable electronics, but the energy storage actually traverses across scales, from the portable to the electric vehicle to the grid storage. Now, as we move across the scales, the predominant design factor becomes the cost. Since we need a lot of battery packs and we need to be worried about the cost of the materials that goes inside the battery. Now, the concern of the cost comes from the fact that the lithium material, which has been used in this traditional lithium-ion battery, has a lot of raw material cost and also is not elementally abundant. So in the next few years, we might be able to meet the supply and demand. However, in the next 10 to 15 years, we are going to be seeing a lot of gap between the supply and demand issues of the lithium. Now, we must wonder, with all the research thrust that has been going on in the industries and academies, why there has been like a huge demand, why we could not keep up with these kind of supply and demand problems, why we would not come up with a solution. So if for that, let's go back and take a look at the roadmap of the battery development. Now, the Volta cell was in the 1800 developed, known as one of the modern battery chemistry. And then there has been a lot of chemistry in between, but the major revolution happened during the 1990s, when the lithium-ion battery was invented, and we got the Nobel Prize in 2019 because of the invention in the lithium-ion battery rechargeable field. Now, we also know that battery is not only about lithium. We have other materials such as sodium could be one option because they are highly abundant and have elemental abundance. Also have the raw material cost much more lower than the lithium market. Now, we might think that it's a new chemistry or new field. However, it's not true. If you look into the graph, actually lithium was developed in the same time as sodium was developed in the same time as lithium was developed. However, lithium got the upper hand because it had higher energy density, and people really didn't think about this abundance and cost solution, cost effectiveness at that time. But then as the supply-demand problem started to show, people again have shown reinterest in this kind of a new kind of materials which could be used as a battery solution for various applications. Now, I have been interested in the work on the metal-based batteries. Why? Because because if we want to go for the low-cost and sustainable solution, we need to reach certain limit of this cost. So here, it has been desired that we get below $100 per kilowatt hour of the chemical cost. Now, currently, lithium-ion battery sits on the line around the 100 kilowatt hour. So we need to go under that limit. So you can see there are like a lot of different chemistries that are available. One important thing to notice here is that all the chemistries at the bottom of the cost line, it involves some sort of metal. Like it could be lithium, it could be sodium, aluminum, but it always involves a metal. Why? Because they are highly energy dense. So if we select a abundant and low cost material, we could go ahead with the low cost and sustainable option. Now, as I mentioned, the 2019 Nobel Prize went to the lithium-ion community. John Goodenough, Stanley Whittingham, and Akira Yoshino won the Nobel Prize. Now, the first rechargeable battery actually itself was on a metallic-based batteries, where Whittingham made this battery. He had a metallic anode as a lithium anode side, and cathode was a titanium disulfide. Now, you might ask why we don't see these kind of batteries nowadays. The major problem they faced was the whiskers that started to grow on the metal side. Now, if this kind of whiskers are growing over the time, they can penetrate through the separator and can go on the other side of the electrode, causing short circuit. And that can lead to the catastrophic failure in the battery. So now, since I'm interested in the next generation, the battery involving sodium, so I wanted to see if we replace the lithium with the sodium, if we are able to see similar kind of observation and if we are able to stop this kind of phenomena. Now, for that, the electrolyte plays a very big role in determining whether you will be getting these whiskers or not. So I have selected 3 different electrolytes, monoglyme and diglyme tetraglyme. And first thing we want to see, how is the cycling behavior? When you make the battery with these electrodes and you put under different electrolytes, whether they are going to be long-lasting or whether they are going to be in the short circuit mode or whether they are going to die. So we looked into the cycling mode on the top panel, and the first 2, basically you do not want any kind of erratic voltage pattern in that curve. So we saw that monoglyme and diglyme had a very stable, smooth performance. But the tetraglyme at the early cycles, it started to show all this erratic voltage pattern up and down, kind of indication of a short circuit. That means we might have the possibility of this kind of a dendrites in this particular electrolyte. Then after the cycling was done, we wanted to see what happened to the electrode, which has gone through the cycling. So we took apart and take the SEM images of this metal electrode, sodium metal, and you can see the metal surface has been evolved differently under different electrolyte condition. The last case showed, I don't know if it is visible from here, had like lot of small dendrites that has been broken and also lot of corrosion in the metal electrode. Now all the electrodes were taken after the cycling was done. We wanted to see what happens in operando. So we have prepared a video microscopy cells. So we already know the tetraglyme, the last case is not good. So we have selected these first 2 cases to show that under operating condition is actually showing a huge dendrites. So it's creating this kind of a mesh structure between these 2 sodium electrode, which is causing definitely the short circuit. Now, in the second electrolyte also, the diglyme case has a similar thing we're seeing. So what we thought is a good electrolyte isn't actually showing this kind of a dendritic growth when you are seeing under the microscope in operando. Now, so now what is the next step? The next step would be to have a co-electrolyte additive and see if we can stop this kind of a dendrite, if we can stop this side of a dendrite. So for that reason, we have added a co-electrolyte additive. That's a common approach. You add a very small amount of other electrolyte with an optimal property in the hope that it forms a stable interface. And in this case, we have selected fluoroethylene carbonate. And as you can see, I think the videos are running. It's not forming any dendrite. So we got what we wanted. We wanted to stop the dendrites so that this metal can run for very, very long time without any catastrophic events. Now, this fluoroethylene carbonate is a very expensive electrolyte, so we are deviating from the fact that we wanted a low-cost battery. So, the next, we thought that if we could replace this fluoroethylene carbonate with something cheaper and which is commercially available and being used in the lithium, which is a ethylene carbonate. Basically, we removed the fluorine part and has ethylene carbonate as a solvent. And we were running these videos, and we see actually, even with the addition of the ethylene carbonate, there was no dendrites. I don't know if the videos are running. Yeah. So no dendrites have been formed for both the monoglyme and the next case as well, the diglyme case. So this is good because we already reduced the cost of the electrolyte, and we also got the performance, at least we were able to stop this dendritic formation. Now, let's take a look at the performance of these 2 cases. So the first case, we were able to stop the dendrites, and we also got very smooth profile. That's what we wanted. Now, in the next case, where we were able to stop the dendrites, but the voltage pattern is all erratic. Like, it's not good. That's not what we wanted. Now, what these results says that stopping the dendrite is not enough. You also need to optimize. So the only thing we change when you change the electrolyte is the interface that's been forming between your electrode and the electrolyte. So what this result is saying that stopping the dendrite is not enough. You need to optimize this interfacial layer by selecting a proper electrolyte to get the best performance. Now I wanted to look into what's going on the interface. So I won't bore you with the details of this analysis, but this is the XPS analysis. case, what we see in summary is that when you have ethylene carbonate added in the electrolyte, it kind of promotes the dissociation of your electrolyte salt. So in electrolyte, you have a salt and a solvent. If you do not want too much dissociation of your salt from the interfacial analysis, we see that too much dissociation of salt when you have the ethylene carbonate, but with fluoroethylene carbonate, it was not there. It was able to form a very good or optimal layer, which allowed a uniform charging and discharging. So with that, our summary is that if you want to enable any sort of new chemistry, you need to look into a customized electrolyte recipe. We cannot borrow all the knowledge from the previous dominant field. And also it is important to look into the cost, the lifetime, so that it could be used for long-lasting applications such as grid storage. And with that, I would like to conclude my talk here. And I would also like to thank my funding source and my advisor for providing me this opportunity to work on this very exciting field. Yeah, thank you. Okay.
Thank you, Susmita, for the amazing talk. So we don't have any time for questions right now, but feel free to catch her after the talks are over. With that, we would be moving to the second keynote speaker, Bhairav Sabarish Vishnugopi. So Bhairav Sabarish Vishnugopi is a doctoral candidate in the School of Mechanical Engineering at Purdue University. He received his BE with honors in mechanical engineering from Birla Institute of Technology and Science in Pilani, India in 2018. His research focuses on electrochemical mechanical interactions and interface stability in solid-state batteries. He is a recipient of the Dow Memorial Student Achievement Award, which was awarded by the Electrochemical Society, ECS, for his research contribution through physics-based modeling, simulation, and analysis. So with this, please help me in welcoming Bhairav for his talk here.
Hello to everyone present here. My name is Bhairav Sabarish Vishnugopi, and I am a fifth-year PhD student in the School of Mechanical Engineering at Purdue University. Before getting to my presentation, I'd like to thank the symposium organizers, Deepanjali Chatterjee, Aditya Singla, and Professor Partha Mukherjee for organizing this wonderful event and also the invitation to speak here. So in today's presentation, I'm going to talk about solid-state batteries and some of the major opportunities and mechanistic challenges that they can confront. So to give a brief context, lithium-ion batteries have garnered tremendous success, as we all know, over the past 3 decades for portable electronics and electric vehicles. However, as lithium-ion batteries are currently approaching their theoretical energy density limits, there is a need to build batteries that have much enhanced performance and safety metrics. The major reason lies in the scale at which electrification and decarbonization is needed in today's world, which includes various examples such as electric cars, semi-trucks, aviation, and also electrical grid storage. So most of these emergent applications require energy densities or power densities that are significantly greater than what current lithium-ion batteries can offer. And in this context, one of the most promising solutions is to replace the graphite electrode in lithium-ion batteries with a lithium metal anode, which has the least electrochemical potential, low weight, and also a high specific capacity. As we see in the plot here, replacing the lithium metal instead of graphite helps us present an intrinsic boost to gravimetric and volumetric energy densities, enabling a wide range of battery chemistries involving lithium sulfur and lithium oxygen, which offer a multifold increase in gravimetric and volumetric energy densities. Coupled with the lithium metal anode, when the liquid electrolyte is replaced with a solid-state electrolyte, which is generally non-flammable in nature, the resulting systems are called as solid-state batteries. And as most of us must have heard this term, solid-state batteries have garnered tremendous research attention and also extensive investments from various parts of the world in the recent years. So in the remaining time that I have in today's presentation, I'm going to introduce some of the key characteristics of interfaces in solid-state batteries and some major limitations that they may potentially encounter. So to start with, the major challenge lies in the morphological stability of the interface between the solid electrolyte and the lithium metal anode. And as opposed to liquid electrolyte systems that offer good wettability of the electrolyte over the metal electrode, solid-solid interfaces are often limited by poor wettability. And these interfaces can also encompass a wide range of heterogeneities and defects, whose implications I'm going to discuss in the coming slides. And in principle, the solid electrolyte or the lithium metal, both of them are not atomically flat. There is an intrinsic roughness associated with their surface profiles, and this requires the application of external pressure in these systems to have good electrochemical contact. And because of the surface roughness of the solid electrolyte and lithium metal, when they are compressed externally, this results in the origin of mechanical stresses. And these mechanical stresses fundamentally alter the ionic transport behavior and electrochemical reactions that occur at such solid-solid interfaces. So this is a key characteristics of solid-solid interfaces, that is, they exhibit a mechanistic coupling amongst the various electrochemical transport and mechanics processes that takes place at these interfaces. And these processes fundamentally alter the way in which lithium is electrochemically plated and stripped at these interfaces. So ideally, we would like to have a layer-by-layer growth of lithium and a layer-by-layer dissolution of lithium when you charge and discharge the battery. However, in most cases, this is the deposition morphology is quite heterogeneous, and this depends on various factors such as the microstructure of the solid electrolyte, the surface profile of the lithium, and also operating conditions. And this is from a recent work that we published related to the asymmetry in plating and stripping mechanisms that are found in solid-state batteries. And I'm showing one of the plots that shows how the reaction heterogeneity scales with the applied current. So in order to achieve fast charging conditions, the regime that we want to be is in high plating rates. However, as we see here, the reaction heterogeneity significantly exacerbates under such regimes, and it results in the formation of hotspots or reaction focusing areas that can lead to the onset of lithium filament growth. And this can potentially result in the occurrence of an internal short circuit. This is again from the recent work that we published that shows that as you increase the plating current, the reaction and mechanical heterogeneity exacerbates at these interfaces that can eventually result in the growth of filaments via the solid electrolyte separator and resulting short circuit. And we delineated a few mechanisms such as contact loss and mechanical extrusion of lithium into the solid electrolyte that are responsible for such failure mechanisms. And apart from these two mechanisms, there have been a wide range of mechanisms that have also been reported in literature, which includes the growth of lithium dendrites through grain boundaries. The pore connectivity of the solid electrolyte plays a major role on the way in which these filaments penetrate and reach the separator or the cathode. And also another key aspect is the heterogeneities or defects that are present at these interfaces. And these can be pre-existing flaws or cracks that are present on the lithium surface, and this induces a very important connection between the manufacturing of these metal electrodes and solid electrolytes with the resulting electrochemical and failure mechanisms. So most of the challenges that I've talked till now is related to the plating or charging of the solid-state battery. However, solid-state batteries have a unique limitation when it comes to stripping. So in principle, with every lithium metal that gets stripped at the solid electrolyte and metal interface, you need lithium to replenish these physical gaps or voids that get generated. And there are some mechanisms such as the mechanical deformation of lithium, or it's known as the creep deformation of lithium, and the diffusion of lithium that can fill these gaps. And the key question is whether this intrinsic diffusion rates can compete with the rate at which metal is stripped from the lithium and solid electrolyte interface. And we see here a video of how the metal interface dynamically evolves, and the red spots here show the occurrence of voids or physical gaps at the solid-solid interface, and these are highly non-desirable because they result in reaction hotspots, and in a subsequent plating cycle, there can be preferential spots at which lithium nucleates and penetrate into the solid electrolyte separator. So unique characteristic of solid-solid interfaces and solid-state batteries is the strong coupling that exists between their plating and stripping responses. And this is mainly through the distribution and fraction of contact area that exists at the solid electrolyte and lithium metal interface. And an important point to note is that the design metrics such as external pressure and current density are quite asymmetric across plating and stripping, requiring us to rethink how these operational metrics are connected with the intrinsic mechanisms that happen. So the last topic that I'm going to discuss is about the safety of solid-state batteries, and the major premise that upon which solid-state batteries are held to be the holy grail of energy storage is that they have a non-flammable separator that promises to enhance thermal stability of the interface. However, in our recent work, which just got published, we showed that non-flammability does not necessarily translate to thermal stability. And the main reason is that solid electrolytes are chemically unstable with lithium, and they can potentially have resistive interfaces, and these interfaces can be of various types. They can be kinetically self-limiting, or they can also be progressive in nature. So the hypothesis that we have is that there is a fundamental correlation that exists between the electrochemical interactions and heterogeneity at such interfaces with the thermal stability of the solid-state battery. And we raised this question in our recent work that whether these degradation mechanisms at the solid-solid interface affect the overall thermal stability of the system. And much to our surprise, the answer was a big yes. And this is an exemplar result that I'm showing in the case of a superionic solid-state conductor, which is LSPS. And we see that there is a drastic change in the thermal signature of a pristine versus a cycled cell. And this is because of the chemical interface that continuously keeps evolving at such lithium metal and solid electrolyte interfaces, which confirms our hypothesis that safety is not guaranteed in such non-flammable solid electrolytes, and rather it requires a detailed mechanistic interrogation. And I will stop here because this work is also presented in one of the posters today, so you can learn more about that during the poster. So lastly, such challenges also exist at the solid-state cathode, challenges including loss of interfacial contact, transport resistance, and also the issue of thermal stability. Again, this is also presented in one of the posters today, so I think conclude my talk here by showing a picture that we recently published showing the mechanistic landscape in solid-state batteries, illustrating some of the challenges related to transport kinetics and mechanics for the lithium metal anode and the porous composite cathode. With this, I'd like to thank all my lab mates who have been great collaborators in all the works that I showed, and a big thank you to also my advisor, Professor Partha Mukherjee, for supporting me through my PhD journey. And I would also like to thank the sponsors without whom this work wouldn't have been possible. So, yeah, thank you all, and if you have any questions, I'd be happy to discuss during the poster session.
Thank you, Bera, for this amazing talk on ongoing advancement in solid-state batteries. So we would now be moving to the final student speaker of the day, Nikhil Sharma. Nikhil Sharma is a final year PhD candidate in the School of Mechanical Engineering at Purdue University, working under Professor K.G. Zhao. His research is focused on understanding the mechanics of electrochemical systems. He performs experimental and computational techniques to study evolution of mechanical properties in rechargeable batteries. Nikhil, we look forward to your talk.
Thank you for the introduction and giving me opportunity to present my work. Good morning, everyone. What I'm presenting today is more part of my thesis, Mechanics and Dynamics of Particle Network in Composite Electrodes. So we know that batteries usually have your anode and cathode electrolyte in between, through which the lithium ion transports and current goes through external circuit. When you do charge or discharge or change polarity, the direction of both of these things change. So comparing with respect to what electrodes were made of during early demonstration around 1800, they used to be just metal plates. But if you compare them with the more recent and commercial electrodes, they are more of a composite, where you have active material which stores lithium. There are carbon additives, binders, which essentially form a porous electrode. This form of porous electrode can either be coiled around to make a cylinder or a prismatic or pouch cell form of configuration. The material that we work for is commonly used as a cathode material, NMC, in lithium-ion batteries. Based on the ratio of transition metal, nickel, manganese, and cobalt, we can tune the properties. In this work, we polished the top surface of cathode and observed it under optical microscope as we charge and discharge. What we observed was there is a change in optical intensity of particles as they charge. This change in intensity is more of what we call asynchronous, because intensity changes randomly within particles. This effect occurs only during the first charge, and we did not observe it during the later first discharge, second charge, or third discharge, and so on. To confirm the repeatability, we tried with different transition metal ratios, different electrolytes, and we used a very slow C rate, like C by 20, taking around 20 hours to charge your battery. Another important thing with the result was, if you look at the zoomed in picture, is the particles which are in the near neighborhood, they don't simultaneously change their intensity. Since there is ample electrolyte here and we are looking at the particle surface which is equidistant from the current collector, we tend to believe that this is because of the carbon network which goes to the current collector from this particle. And in literature, as well as our previous work, we had already seen that carbon binder does not completely cover NMC in modern commercial batteries. And there is a lot of voids and holes, and there is very non-uniform carbon binder network. So based on that, we made a very simple model where objective was not to replicate the experiment, but provide the mechanistic understanding. If you look here, the black is our carbon binder domain, which is electrically conductive. The gray are our NMC active material particles, and we have 5 particles going from left to right. They have increased electrical resistivity due to the NMC particle, which breaks down the continuous carbon binder network. This thing becomes important because inherently NMC, our active material, has around 4 to 5 orders below electrical conductivity as compared to the black carbon binder domain. So that's why even for the particles which are nearby, based on Butler-Warmer relation, we find a lot of variation in the phi s, or the electric potential. This essentially creates the asynchronous behavior. Now the second question becomes that why this asynchronous behavior just persists in the first charging process. And in order to do that, we looked at the diffusivity values of NMC, and similar to electrical conductivity, we find that it varies by 1 or 2 order during the initial time when lithium is taken out. This essentially creates a situation in which it is easier to take lithium out of NMC, but it is very difficult to push it 100% back. So when you start for the first charge, you are at low value of electrical conductivity and diffusivity, but after that, you are not able to achieve your pure pristine state, and you inherently start from the higher values of both the things. So asynchronous behavior kind of diminishes. This is our lithium concentration profiles. Vertical is the idealized concentration for topmost particles, and horizontal axis is the time. During the first charging process, there is a lot of variation of concentration among particles. During the discharge, it converges, and then again, it is relatively minor degree of asynchronous behavior. Going from this small cyclic behavior to looking at the long term. In collaboration with our collaborators from Stanford, this is a 3D high energy X-ray holotomography image, which gives a lot of details about particle damage, particle morphology. The resolution is really good, around 20 nanometers. Based on 2,000 particles that we studied for this, there are 2 data points that we focused on. Number one is how particles damage is related after 10 cycles, and second is how the damage is related after 50 cycles. So during the 10 cycles, which is the green one, you can see that the most contribution score towards damage is provided by the particle's own local characteristics like sphericity, how much is the volume to surface area ratio, and how much is the homogeneity that is present. But as the electrode moves towards higher rates, like after 50 cycles, the blue parameters provide a much more contribution, which is more of a group behavior nearby, like how much is the distance to nearest neighbor, how much is the packaging density, and those kind of things. So this transition from particle level things to a group behavior is something that we wanted to model. And since there were more than 20 attributes here that we could do, we just wanted to first demonstrate that interplay between electrochemical activity and damage can very easily explain this. So this is just a very simple 3-particle model. Particles are same morphology, they have isotropic chemical, mechanical properties, but the only difference is the surface area. The reaction surface area is very different in all 3 due to the amount of high conductivity carbon binder. During the initial cycles for both concentration and damage, we observe a similar diverging behavior, but slowly it homogenizes. So this gives us much more information about how electrochemical conditioning occurs in electrodes and how during the initial start stage after the manufacturing, they go from particle localized activation to more of a electrode synchronized behavior in terms of damage. So these are my summaries, and if you want more details, you can go through our group's website, and if you have any questions, just let me know. Thank you.
Question we will be doing afterwards. Okay. Thank you, Nikhil, and all the other speakers for the amazing talks today. So this concludes the first part of the symposium. And now we would be starting poster presentations. So we have some really amazing posters today on electrochemical energy storage. You can stop by, interact with the poster presenters, the speakers today, and even with other fellow student researchers. And we would be also starting lunch now, so you can grab the lunch. And let's move to the second part of the symposium. Thank you all for attending.